Do you guys have any questions? Yeah. The assembly code examples should all be up there. So like if you just go to like the examples folder on the Google Drive, everything should be there. It might not be like our exact version, but versions that we've done previously in the course, because our exact version isn't there because the gedit doesn't behave nicely with the Google Drive and doesn't like to save the files there. But there should be some versions up there already for you to look at. Anything else? Okay, so last time we left off, we were trying to find the length of a string, but we wanted this to be done through like a function, which is going to be a subroutine for right now, and we'll talk about what makes functions a little bit different from subroutines, hopefully today as well. So when we were writing our subroutines, we had to figure out two things, or actually three things. Thing number one, how should we pass values to our subroutines? Thing number two, how should we return values from our subroutines? Thing number three, who's responsible for saving the registers that I happen to use inside the subroutine? So, what were our options for passing values to a subroutine? Yeah, so we can either put it into register or put it into memory, right? To passing it, and the same thing for returning, either put into a register or put into memory. But just let whoever is going to know, who's ever going to use your function, know how to use your function. And then if they use it right, everything should work out fine. The other thing that we need to consider, though, is our function, right, or our subroutine, it might use other registers besides the ones that are used to pass in arguments, right, or to return arguments. So whose responsibility should it be to save those registers? For example, if my register just happens to use EBX, but EBX isn't an argument or a return register, who should have to save that register's value? Well, what are our options? Who could potentially save that register's value? That's where you can save it, is in memory. But who should save it, not where should we save it? Because yes, it will be saved in memory. The subroutine could save it, or the function, or the subroutine that calls the subroutine, right? So either the caller could save it, or the called subroutine could save it. It's up to you. But if you decide not to save some registers, let whoever know that's calling you that your stuff, these registers also need to be saved as well. So this was the code that we need. Yeah.
So are you saying that you would move it in the subroutine or move it in the actual memory?
Correct, right? So like either before we do the call, right? If this function was planning on using like EBX, we could save EBX because we know that subroutine is going to overwrite it. Or we could not tell the caller that we're going to overwrite the subroutine, or not tell the caller that we will overwrite EBX, but instead save EBX before we do anything with it, overwrite EBX and use it as what we want, and then before we return, restore it back to its old value. So to the caller, it looks like nothing changed. Does that make sense? So let's go with option number one, the caller, or the called subroutine should save it. But this is the code that we need to translate. Just got more or less one line of code here. So how do I translate this line of code? Yeah.
What is the difference between strlen, RET, and strlen NDM?
So the strlen reg subroutine, we're accepting our parameters through registers and we'll return them through registers. And for the memory one, we're accepting our parameters from memory and we'll be returning the answers in memory.
So both are like different functions.
They're doing the exact same thing, but the implementation details are different.
Right.
So they're both solving the same problem, but how they're doing it is going to be a tiny bit different. It's just pretty much how do you accept and return parameters is the only difference. Yeah.
Can you verify the difference between a subroutine
So basically, like, subroutines are functions for the most part. It's just that if you want to write C-style functions, there's a couple of rules you have to follow. But other than that, it's the same thing. So how can we translate this line of code? Right? We've done for loops. Hopefully you've done some for loops also in your homework assignment. How do we translate for loops? What do we have to do first? I think there should have been a line of code that we need to do first, which is len is equal to 0. It's the first one, actually. Oops. Or maybe we can just put that here. So how do we translate this?
You can store 0. It's like memory before memory.
Well, remember that we're going to be returning len, right? And so the return value we said is going to be placed in EDX. So what register should we choose to use for len? Yeah, the EDX. So move L $0 to EDX, right? This is len is equal to 0. What do we do after this? Start the for loop. So how do I start the for loop? Okay, what label do you want to use? Right, so one kind of like risky thing about just using like start for, right, is that, you know, we're going to have another for loop over here, but the labels kind of have to be unique, right? So you might call this one something like stir len reg for start. I know, it's a long name. But then we can also have the end label as well and spell it correctly for end. Okay, so we have our labels now. I'll let you know that like the null character, it's just 0. Right? Because next we have to do our if statement. All right, or at least the condition portion of the code. So when we're doing a comparison, all of our comparisons have to be against 0. But hey, guess what? This one already is against 0. Right? Because the null character is 0. So how do we do this? Well, so we might have like the negation. So we want to do like stir len is not equal to like the null character, right? But we still need to do kind of like some operation on this to actually compute it. So the next thing that we would do would be like stir len, you know, minus the null character, which again is just 0. Is it not equal to 0? Right? And then the negation is it should be equals 0, right? So the first thing I need to do is the comparison, the stir at len minus the null character. Again, null character is just 0, right? I guess if we want to be like extra fancy, we can do that. Dot EQU null is 0. We can say null if we want to instead. So how do I do this right here? So should we use, so okay, CMPL?
Or not L, should be something else.
Yeah, because we're comparing characters, right?
Yeah.
So it should be B, right? I'm going to comp B. What should be our first thing?
It would be, so the D is not constant, so we use O for the str. So it would be percent ECS inside the parentheses. And then it would be Leonard percent EDX, comma 1.
Okay, and what do we want to compare this against?
0, O. it should have been CMPD $0, comma that.
Yeah, exactly. Right, and so we called null, right, from back here,
Oh, all right.
right? It's just 0. Oh, I guess I should also mention, like, if you guys are doing your homework and you see some things like you can't, like, de-randomize memory, you can safely ignore that. It'll still work. Anyway, so we do our comparison, and then what should we do? Jump what? Jump of equal to, right? Get out the loop. And then we need to do our plus plus len, which is just increment EDX. And yeah, we're done. That was it, because that's all the things that we have to do in the for loop. There's no body. Any questions here? And again, what does the ret keyword do? Yeah. Oh, yeah, thank you. Jump to the start. Go back to the next iteration. Correct. But what does the ret instruction do? Takes you back to not necessarily main, but wherever you were called from, right? But remember, the ret instruction by itself does not return a value, right? How did we return a value from our subroutine? Yeah, we just put it into a register, right? And so whoever called us, they should look in EDX after they finish calling us for the answer. Does that make sense? So what happens if we do this, but now instead of stir being placed in ECX and the return value being in EDX, we want to put them into these locations. What's going to change here? Again, we still have just this one line of code to translate. But now, again, the only difference from what we did before and what we did now was that the arguments are passed in a different spot, and the return value will be passed in a different way, right? It's going to be passed through memory for both of these things instead of being passed through registers, right? And we already made those labels back up here.
So it's the same thing because we put EDX.
Can't quite do that, right? The other, you'll like, let's say we did just do as was suggested, and we just switch it up, right? So everywhere you see ECX, you want to replace it with stir len stir. So you want to take this out of here and take this and put it in the front like so, like that. And then you want to change this. Oh, well, that's now a label in memory too. So stir len ret, I guess, goes here now. Well, but again, this is a variable amount, right? Len keeps changing. It's not a constant. And then you want to change this to be that. And then I guess we need some labels here, don't we? Did I copy everything? Not quite. Will this work? I guess this one should be will this work? Yes, it will work. No, it won't. It won't quite work. There's definitely some stuff that's wrong with it, right? For example, I think it was kind of already mentioned out. What can go into the offset field? What's allowed to be here? Registers. Is that a register? It's a constant, right? So that's definitely not going to work. So we're going to have to still use some registers in our solution. The other thing to think about too when you're writing your assembly code is that it's much faster to access registers than it is to access memory. So as much as possible, you'd like to work with things in the registers and then move them out to memory when you have to, or move them in from memory when you have to. So constantly having to access memory like every single time, like here, is a bad idea because you have to keep doing it over and over and over and over again instead of just having it in a register where you keep updating it and then move it to the end. So we're still going to need to use some registers, right? What registers do you want to use? What? Can we keep the length in a register? Yeah, sure. Which register do you want to put it into? Well, again, yes and no. No, they're both free and not free because it depends. Right now we're in the situation of we want to use some registers, but we now have to come up with some conventions. Should our caller save these registers? Or should we be forced to save these registers before using them? And for right now, we're going to go with we should be responsible for saving those registers. So any registers we want to use, we're going to have to go save them out to memory first before we utilize them. Sound good? So what registers do you want to use for len? Any one will do. You just got to pick one. So sure, EAX will be len, right? And we will also actually are going to need stir too. Because even if we replace this now with EAX here, gosh, come on. This with EAX, this is still wrong. Do you know why? Or I should say, what is the equivalent line of C that this code translates into? Discuss amongst yourselves. Line 61, it's wrong. It doesn't do what we want. What does it actually do? What's the equivalent line of C code that this is actually implementing? Discuss. Yeah, I didn't switch that one up yet. I forgot. So do we have an idea of what this is actually doing in C? Any thoughts? as to what this line of code actually does, because it's not doing stir at len. This line right here is doing something along the lines of the address of stir at I-ish. Because remember, stir len stir, right? It's going to hold the value stir. What is stir? It's a pointer, right? So stir len stir, right? It must be it's a pointer. It's the address and the area of memory that holds the pointer. So it's like a pointer to a pointer, right? So that's what's wrong here. The other thing why it's not quite exactly at I is because we're only going like 1 byte past that pointer. So instead of going over to our actual string that we're going to pass in, my string, and then going through the characters that are here, we're going to go up to my string and then start going down this way. It's fun times. So be careful with that. Make sure you do the right thing. And again, once we switch it to do what we want to do, oops. All right, don't do that one. We are going to be using EBX for stir. And then we're more or less done. Except, again, these registers these registers we're assuming are currently in use, so we have to save them. So how can we save EAX and EBX given that I have old EAX and old EBX labels now? Move out.
Register comma label.
Yeah, EAX to old EAX. Move out EBX to old EBX, right? Save the current values of the registers, right? Now we need to go load them in. So how can I make EAX be equal to len? How can we do that? So we need to move L what into EAX? Yeah. $0. Right, so this is the EAX. Oh wait, we already had that down here. So I guess we're fine there. How can we make, I guess we should change this line to make EBX equal to stir. So what should we put here? Stir len stir, right? Go to that location in memory and copy the value that's there. Copy the pointer. Yeah.
So you're using the old labels to be the first current state of the registers before you upload.
So we're saving the value of EAX and EBX because we need to use these registers, and these are the values of whatever happened to be in them before we were called. Right? I don't know exactly what's there, but there's something there. Probably, maybe. Let's make sure I save that first. Right? So we save the old values. We make EBX be equal to stir, right? We set len equal to 0. We do our whole, rigmarole. But what do we have to do before we return? Well, first thing we have to do is set the return value, right? Because the return value is not where it's supposed to be. The return value needs to be placed into stir len ret. So my return value is EAX, so move L %EAX to stir len ret. Great, that's set. And now we need to restore the registers we used. So, right, put them back to what they used to be. How can we do that? Yeah, like move all old EAX into EAX, move out old EBX into EBX. Any questions so far? Yeah. So again, $sign is constant. And if you put a $sign in front of the label, the constant part of the label is it's where it's located at in memory. So it's like essentially the address of that thing. Whereas if you don't put the $sign there, it's going to be using the advanced indexing mode, but it will only be giving the displacement field, right? So again, if we think about like the $sign as being constant, does this make any sense? At that address? Well, I mean, like currently kind of what this line of code is saying to do is the address of old EAX is equal to EAX if you have that. Does that make any sense? Again, like if your variable x is at address 100, when you do ampersand x, you just get the value 100. So now you're trying to say something like 100 is equal to 5. Or 100 is assigned the value 5. Just because this does mean the address of this variable, if you say the address of the variable is equal to something different, it's nonsense because you can't physically move that value by doing this statement, right? The other thing to think about is this is a constant, right? So we're trying to say set some constant equal to some value. Set 7 is assigned 5. Doesn't make any sense to do something like that, right? Which is, if we go backwards counter, which is why we wouldn't have $signs there. So again, you have to be really careful with what the $sign really means. It means treat this thing as a constant, right? The constant part is where it's located at in memory. So you're literally trying to edit the address, so that address is no longer address 100. It's now address 5 or whatever happens to be in EAX. Oh yeah, totally. When you needed the address of the variable. Right? For example, with pointers, right? If you did something like this, so let's say we don't want to do that anymore. So let's say we did something like this. Move out $sign old EAX into ECX. What is the equivalent line of C code here? EX, right? Which if you think about it, this is something like treating ECX like an integer pointer ECX, right? So you can hold an address, and now if we did something like this, move L percent ECX into say percent EDX, that's doing something like EDX is equal to star ECX, right? You dereferenced it. So yeah, I mean, there are totally times where it makes sense to do something like that. But you might not want to do it all the way. You will see an example in one moment where we do pass the address of something in. And we do it legitimately. Any other questions? Yeah. So EBX is going to be like a char pointer, right? But remember, string itself, the char pointer, was stir, which is the character pointer, was placed into strlen stir. So at strlen stir, there is a pointer to the string.
Okay, so let's see.
Well, because a pointer is in, right? So we were accepting an address in the first place, right? So if we're saying that strlen stir should be, you should place stir into strlen stir before calling me, you need to place an address there, right? Where does this thing happen to be at in memory? Where is the string at? And again, you'll see an example in one moment of us actually calling the function and things happening. Any questions? And again, for the calling, hey, look, when we wanted to do the first version with strlen reg, what did we put into ECX? We put in my string, right? But notice, $sign my string, right? A pointer to where the string actually starts at, its address. Which I think answers both the questions you just had, at least with a small example, right? And then we call our function, and then our answer should be in EDX. So let's try compiling this and see if it works, or if I made some mistakes. So remember, AS --gstabs --32 -o stir len sorry about that .o stir len .s, and then linking ld -m elf underscore I386 -o stirlen.out from stirlen.o. Okay, great. So now we can run this in DDD. If you're ever curious about how the heck I figured out what those extra command line parameters were to compile in 32-bit mode were, I had to go look at the documentation for the assemblers and the linker to figure that out. So do some Googling, and then I found my answers. So let's set a breakpoint at, say, our call, which is on 96. So break it, 96. Let's go run our program. So fantastic, we're down here. And so we do our next. So if we look at ECX, graph, display, $, $ECX, it's 0, right? After this, we get some crazy huge number, which makes sense because it's an address, and addresses are crazy huge numbers. And then we go into our program. So we move 0 into EDX. So we'd probably like to see EDX. So graph display $EDX. That's there. Oops, I don't want to do that a second time. On display. So next. So now we need to do this comp B. What would be really nice to see right now in doing the comparison? What would be really nice to see the value of what like string at I is, like ECX at EDX. And you can totally see that. So we'll do graph display. And again, we'll do some creative casting. So char pointer. So ECX, what is it? It's a character pointer, right? That's what's stored in there. And we'd like to see our character pointer at what index? EDX. Hey, there's the H. Right, so I just cast it to like make these displays of the arrays kind of work. You have to cast back in the types of the registers or labels to then be able to access them. So if we go through, we have H. It's not the empty character, so we'll add one to our length. E's not, L's not, L's not, O's not. Here's our null character. And we're out of here. So we go back, and what do we have in EDX? Well, that's the length. Any questions? You want to see the other version where it calls it with the arguments in the registers? So first things first, we'll put some values into EAX and at EBX just to show you that they don't get changed. So we'll move L $700 and blah 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 into EAX, and we'll move L something into EBX. So now we need to do the call to our new guy, right? So we need to call stirlen mem. But before we can call stirlen mem, what do we have to do? Yeah, we have to pass the arguments, right? This guy right here is, right, pass the arguments, call the function. So here we need to, this is again calling the function, and then we need to pass the arguments still. So how can I pass the arguments now? I need to move L $ my string into where? Oh, what does our documentation say that we should do? The string should be placed into stir len stir. So I should go put this into stir len stir. Right? We go and put it into memory, and then after we're done, the result is going to be in memory at the location. So we'll see that happening at stir len ret. So oops, come back. Ooh. Gosh, stirlen .o, stirlen.s. So you can like run commands from the shell here by just typing shell first, then the command. So ld dash o or dash m elf underscore I386 dash o stirlen dot out stirlen dot o. And then here we can say source reload source since we've recompiled it. Right, we need to get that new stuff in there. And then we're also going to set a breakpoint on line say 102. Did you not reload? Maybe that doesn't work. If that worked. Break on 103. Break on 103 should be fine. So if we run our code, if we print or graph display $EAX, that's some value, graph display $EBX, it's the weird value you put in there. If we do it with EDX, it should have 5 in it, which is the value that we computed before. And then we're also going to want to graph display stirlen ret. Okay, apparently I need to give it a casting to make it be happy. So cast it to an integer. Which direction? To the right slightly. Oh my goodness. It's just barely being cut off, isn't it? That didn't fix anything, did it? It's there, and then like so. Okay. There we are. Now let's go and we'll call our function. So we pop into our function. So we save our old values. And then we're going to want to look at EBX. So EBX gets some funny address, just like before. We're going to put our length in there. And again, we could do the command to display the characters, which was graph.
Question?
Yeah.
Is it possible to GDB when your code can't compile?
No.
Okay.
Because again, the GDB or DDD, it's running your code. And so if your code is not runnable, it cannot run it.
Okay.
Char pointer $EBX at $EAX. So again, there we have our H, and we're going through and we're getting our letters again, and everything's fantastic. Great, that's 5. So now we're going to put EAX into strlen-ret. Boom. Right, it's there. And then we're going to put the old value of EAX back in there. Put the old value of EBX back in there. And then we go back to where we're called from. And look, we can strlen-ret it has 5, which is exactly what we wanted. Given our current setup, what types of functions could we not implement?
What?
No, void are fine, right? We just don't have a return value, so the calling function is not going to look in a register for the return result. Right, and if it's void in terms of no arguments, but we're just not going to put anything in there before we call it, right? You could do a callback function if you wanted to. You just pass in the function in there. If you want to see how that happens, all you do is you put like the address of the function into EAX or some other register, and then say call the register instead of call the actual label. So that's fine. What's everyone's favorite type of function? Recursive functions, right? The problem right now is we couldn't do recursive functions because we do not know how many times we would call ourselves, and every time we'd call ourselves, we would need to like get new values, which probably would overwrite the old values. So there's no way of like storing that information as we go down for the number of times that we're called. So we couldn't do any recursive functions at the moment with the setup. But we're about to talk about the stack just a tiny bit more, so we'll get into what it is that you need to know. So let's pop back over here. No. So let's talk about the stack in Intel, right? You guys are familiar with the basic concept of a stack. You've covered that in your data structures and algorithms course, or you've seen it somewhere. Is anybody unfamiliar with what a stack is? Never seen it before? Okay, then we'll definitely talk about it. So a stack, just in general, then we'll get back to stack in Intel. So a stack has first in, last out behavior. First in, last out. In terms of how it's behaved. So the first element added is the last element removed. Right? The way to kind of think about this is, nope, not that. Nope, not that one. To get rid of my picture. It's like a stack of plates, right? That first plate that you put on, right, at the bottom, it's the last one that you take off. Or as you add plates on top, right, those ones will be taken off before the plates that already existed. Beautiful picture, right? The few operations that you can perform on a stack are push elements, which means add an element to the top of the stack. Pop, which removes and returns the topmost element of the stack. And then there's like peek, which is just look at the topmost element. Any questions on how stacks behave? So, stack and Intel. So for the stack in Intel, the top of the stack is pointed to by ESP. So ESP is the extended stack pointer, and it always points to the top of the stack. Wherever ESP is pointing to, that is considered to be wherever it's pointing to, that's what's considered to be the top of the stack. This is why I said don't use ESP as a general purpose register, because if you start changing ESP to some just like random value like 7, the computer now thinks the top of the stack is 7, which is probably not where the top of the stack begins at in memory, right? What is considered the weird thing about the Intel stack is that the Intel stack grows towards 0, which means the top of the stack is at the lowest address, and the stack itself to be wherever ESP points and all addresses higher than that. Does not need to be that big. So over here, right, we might have like our address. Here's our value, and then over here we're gonna have ESP. So over here, once this, it'll look a little bit prettier in a second. Trust me. Just have to knock some things off. Normally this would be something I do on the board, but things don't get recorded, so that's why we're doing it here. So we might have like our address is 100. And then one other thing that we should also say is all accesses to the stack have to be word size. So when you're accessing things, kind of like when you're pushing or popping off the stack, they have to be in multiples of 4 for a 32-bit. So we'd have something like 100, 96, 94, 92, because I can count, 88, 84, 80, 76. And again, we might have some values here. Here's the value 50, here's the value negative, something, 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 more things. Oops. And let's say ESP right now was right here. In our example, first question is, what value does ESP, oop, that one got funny really fast. How's it that shrinking the table made it get funny? Okay, that time it worked. So first question is, what value does ESP have right now?
84.
Yeah, it has 84, right? Because it's pointing to the top of the stack. Which element is considered to be on the top of the stack?
36.
36. And what is considered to be the entire stack right now?
76 to 84.
Not 76 through 84. So notice this point right here. It's considered to be wherever ESP points and all addresses higher than that, right? 80 and 76, they're lower than its current value of 84. So actually, these elements up here are considered to be what's part of the stack. Yeah, Mira?
What do you put on the stack? Like, I get that these are addresses, but why did they get added to the stack? What function do they serve?
Like, what's the point of the stack?
Well, like, I guess I know what like you talk about what a stack is in theory in the land of data structures, but this seems to be a much more specific stack.
Yes, so this is like your function call stack, right? Because if you remember when we talked about memory at the beginning of the class, there's 4 sections: text, data, stack, and heap, right? You've already seen how to do 2 of them in assembly, the text and the data, right? .text, .data. Now the stack is the 3rd section of memory that we're talking about right now, and that's where your local variables and arguments go, right? It's where it's your automatic memory. And so that's what we're working with right here, because the things that will be saved on the stack will be locals and arguments, as well as the return address that we want to go back to. So any questions so far? Okay. So let's talk about some of our stack instructions. The first stack instruction that you've already seen is call. Right? So call label. So over here with calling on our label, this does 2 things. The first thing that it does is it pushes, or I should say it saves the return. Well, actually, let's do them in a different order. There is push value. And what push value does is it adds, value to the top of the stack. Yeah, I knew you would do that. Oh, okay. No, go back to being normal size. Okay. Right, so push value adds value to the top of the stack. So let's say we did something like push $58 to the top of the stack. What's going to happen here to make that push happen? So everything has to move. So the first thing has to happen with ESP. What happens with ESP? It's just not a trick question, right? So we want to add 58 to the top of the stack, right? So we don't want to change this 36 to a 58, but we want to put the 58 on top of the 36. So how can I push that value? What's going to need to happen over here? But again, I can't move things in memory, right? Below location 84, there's always going to be location 80, right? So if I want to push 58, where's that 58 going to have to go to? It's going to have to go down to 80, right? So our 58 is going to have to come here. And then what needs to happen to the stack pointer? Not increments. Decrements, right? Because we needed to move from 84 to 80. So it goes down here now. And we've now added 58 to the top of our stack. Yeah, just completely overwrites what's there. So we went from having 47 there and it not being considered part of the stack to having 58 and it being considered part of the stack. Does that make sense? Any questions so far? I guess this should probably be more generalized as like push source. Add source to the top. Source can be a register or it can be a location in memory. Right? Or a constant like we just did. Does anybody else need to see any other examples? Yeah.
When you call push source, does it automatically detect the
Yes. Right. So
you don't have to do it yourself, or
you don't have to do it yourself, right? But so like when we push source, if we think about the implementation of push source, if you had to push the source, right, but you were not allowed to use the push instruction, how would you rewrite push? How would you write push without using push? Right? Implement push using other assembly instructions. What had to happen here? What were your two steps? What did you do?
change the value at location 80?
Yeah, but is it always going to be location 80?
You find the address of the topic.
Well, the rest of the top of the stack is in ESP, right? It's always ESP, right? So we took the stack pointer from here, right? Oops. We took it from here, right? And we moved it down to here. How can we make it move down? Subtract how much? On a 32-bit machine, pushing will always be a subtraction of 4. It'll always be a word size. Now, if you're doing a push in like a 64-bit machine, we'd be adding 8 bytes worth of space every single time. If it was on a 16-bit machine, we'd only be doing 2 bytes worth of space. So it depends on the word size of the machine for Intel. Right? Right. So the first thing that we need to do would be sub L. Yeah, like $ word size from. Yeah, from ESP, right? This is gonna make space, and then, right? So right, we moved the ESP down here. So ESP is on line 80, and now we need to put the 58 there at that location. Move L. Yeah, $58 to percent ESP. Are we happy with this? What? $sign ESP, is that what you said? We can't put $signs in front of registers. We can put percent signs though. That's how we denote that they're registers. $signs are only in front of constants. Put nothing in front of what? Oh, if we just had ESP instead of percent ESP, it would be looking for a label with the name ESP. Of course, we don't have one. Yeah. Are we happy with this? We have to dereference ESP, right? Because right now we're saying ESP changed to 58, right? Which would make the top of our stack be 58, right? It's actually going to change its address to be somewhere way, way down there, right? But what we actually want to do is we want to go put 58 at the location that ESP points to. So, parentheses, ESP to make that happen. Right, go to where ESP points to. What address does ESP point to? It points to address 80. Go to address 80 and put the value 58 there. Does this make sense? Of push source. And if we wanted to generalize it, the 58 turns to source, so move source. Whatever source happens to be there. Yeah.
If we wanted to like save the value that was there before pushing, would it just be like the same thing, like moving the percent ESP?
So you want to save like the values that are below ESP?
Well, like when we push 58, we change it like from 47 to 58.
Mm-hmm.
Like if we wanted to save that value.
So normally, like the elements that are considered below, like, or at addresses below the top of the stack, they're considered just be garbage because this is where the stack's going to grow into, right? So this is like available memory to be used by the stack later on when it needs it. But if there are values that happen to be there, they were from old calls, but they're no longer valid. They're no longer good. It's just garbage stuff there.
So like our normal text instructions, they don't like interact with this part of memory.
So correct. The stack and the text are stored in different locations in memory. Yeah.
This kind of side question, but what does it look like if it's, like, what is it considered when a cell has none? Like, is the only way to have nothing is 0?
What do you mean by nothing? Because every location in memory has something. The value might be undefined. It's something, but I don't know what it is. But there will be something there. Yeah, totally, right? If you don't initialize the memory, it's whatever happened to be there from last time. Right? Or whatever, like, the computer decided to randomize it to. It's just something there. I don't know what because I never said what it should be, right? So if I do, like, int x, and then I print out x, what value I get, or I don't know, right? We didn't say what x is supposed to be, but it's going to be something. Does that make sense? I mean, generally, like, your other question, like, what does nothing mean? A lot of times 0 is considered to be nothing, so yeah, you would, like, 0 everything out to say that there's nothing there, but I'm not sure if that's your question.
When, like, your computer says that there owns some space, I mean, everything has some kind of actual meaning stored. How does it know when something that's stored is meaningful and something's, like, random and nothing?
Okay, so the operating system is the one that manages the memory accesses. So every time your program asks for memory, the operating system is the thing that gives it the memory. And so it keeps track of in tables, like what memory is currently in use and what memory is not. And so the operating system is the one that tells you, like, you're almost full. Right? Because it started out with, like, everything being empty. And then as people ask for it, it's like, okay, here's some memory for you. Here's some more memory for you. Here's some memory for the other guy. And then when they were done with it, it's like, okay, I'm going to take that memory back and mark it as being unused. Right? But if people keep asking for more and more memory and they never let go of any of it, then you run out of memory because it's all being used up. Any other questions? Okay, let's talk then about pop. So let's say we want to do pop into some destination. I guess this one should have been something like adds source to the top of the stack. And then pop dest will remove the value from the top of the stack and place it into dest. So here, you might do something like pop %EAX. What do you think is going to happen when we do pop EAX? Given our current example. So remember, EX has some value, but remember, pop doesn't say, what pop says is take the value on the top of the stack and place it into the destination. Take the value off the top of the stack and put it into EAX. So after we do this instruction, EAX is going to become what value? You said 80, you said 58, right? I just said 50 the first time. It'll become 58 because what value is on the top of the stack? 58. So we're going to take that value off the top of the stack and we're going to put it into EAX, all right? So EAX is going to be equal to 58 from doing this. But now, how do we remove the element from the stack? Right? So we need to take ESP and move it where? Yep, great. We took it off the stack. Right? Because again, the stack is considered to be what? The stack is considered to be wherever ESP points and all addresses higher than that. If I take ESP and move it up to 84, is 80 greater than or equal to 84? No, so it's not a part of the stack anymore. Right? But that value, yes, is still like hanging around there, right? Because we're not going to waste our time clearing it out. right? And when we need to use it again and we push something back on top of it, we'll just overwrite what happens to be there, right? So this would be like EAX is equal to 58. Oops, I guess the numlock turned off, 58. And if we did something like pop EBX, what would happen now? EBX is going to be equal to 36, and then what happens to ESP? Goes up to 88. And then if we clear out the highlighting, right, those guys are no longer considered to be part of the stack, but they were at the beginning. So how could you implement the effect of pop destination using other assembly instructions? What are we going to accomplish here? How do we do it? Okay, so move L %ESP, right? Take the value that's in the top of the stack and put it to the destination, right? Whatever destination has to be, right? We're generalizing, right? So dest equals top of stack. Now you need to, second step is remove the element. Yeah, word size 4 to ESP. Remove element. There's a question over here? Because again, if we don't dereference ESP, it says take what, sorry. There, is that better? So if we don't dereference ESP, right, it says take what ESP is and copy its value into destination, right? Where we're down here at the beginning, right, ESP, its value was 80, right? So if we didn't do the parentheses, we'd end up with 80 in EAX instead of 58. Oh yeah, sorry. This makes sense? Now, what about peaking? What would you do to peak? Look at the top element of the stack. If you just wanted to look at the top.
Just do the first line without the data.
Yeah, just do this first line, right? Do the move L, right? If instead of peeking at the first element, you wanted to peek at the element that came before it, right? You wanted to look at the second to topmost element. Not quite, because again, what does this stack kind of look like? What's it look similar to? It's an array, right? So here, right, this element, if we go pop back up here, this guy right here is the stack at position 0. This is the stack at position 1, at 2, at 3, at 4, at 5, blah, 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 right, all the way up. So if I wanted to access the second element, right, we'd basically be doing like ESP at 1, right? So all we'd have to do if we wanted that effect to happen over here was we'd do something like 4 in the front, right? Word size in the front, and that would give you the second element. Or if you wanted the third element, you would do 8, right? Basically, the index times 4 times the size of the element will get you which one you want past the first. And there will be times where you need to do that, right? When we start getting to the functions and how they're implemented. Okay, now let's talk about call label. So what call label does, so first question for you guys is, what's the difference between calling and jumping? Right, because we have call label and we have jump label, right? Both of those things do what? They take you somewhere, right? But the difference between them is when you call something, you're able to return later on, right? And so if we want to return later on, wherever we happen to be called from, what are we going to have to do? Store what? Store the address of where to go back to, right? Store the address of where you're called from. So when we do call label, we have to do two things. First, save the return address. Where should we save the return address at? Where might be a good place to put the address on top to? On the stack, right? So save the address, right? On the stack, right? And then, after we save the address, we have to go there, right? Go to label. Right? So save the return address on the stack, and then go to the label. That's what call does. It's a pretty simple function. Save where I want to come back from, save where I want to go back to, and then go to the place that I want to go to. Right? So how might we rewrite this in terms of assembly code? Right? Write the assembly equivalent of this. Right? So we can assume that we're doing something like this. We want to translate the following line of code, right? Call fun, right? And then down here you might have something like, next instruction, and then, we do whatever that line of code that comes after the call. So how could we translate that and do the same thing, but using other assembly instructions? Fun is some label somewhere else, right? That's the function that you're trying to go run. So step number 1, how can you save something onto the stack? You push it, right? And what exactly do we want to push? So we want to push what? So what does it say that we want to save here? It says that we would like to save. Do we want to save where fun is at, or do we want to save something else? Because we want to save the address of where we're supposed to go back to, right? After fun completes, where should we come back to? The next instruction. So what should we save on the stack? So we're going to push. Yeah, it does need to have the $sign there. Right? Because what would happen if we just did push next instruction instead of push $sign next instruction? Yeah, we would save the instruction itself on the stack instead of saving where the instruction is at. Does that make sense? Save the actual instruction. Like if this next line, the next instruction was something like add 5 to somewhere, we would actually store the instruction add 5 onto the stack instead of saying, oh, the address of this instruction. Step number 2, go to the label. How do you go to a label? Yeah, jump label. And we're done. That's all call does. Saves the return address. You go to the new place you want to go to. Right? But it's a little convenience function. So you have to keep writing that all the time. Any questions here about what call does? Okay. What about ret? So what does ret cause you to do? Yeah, it's return back to where you were called. Sort of. It's not quite technically happens. You can think of it as. That's not actually what it does, right? A return call should always be paired with a return instruction should always be paired with what other instruction? A call. And what did the call instruction do? we put something onto the top of the stack, right, where we wanted to go back to. So if we're going to return, what should we do? Take the thing that we put onto the stack and go to that location in memory, right? So remember, the instruction the register that keeps track of what instruction that you're currently doing is EIP. So we want to take what's on the top of the stack and put it where? Into EIP. Because if we put the address into EIP, that's going to cause us to go to that location in memory and begin execution there, right? So what it really does is it takes the value off the top of the stack and places it into EIP. Normally you don't have, like, I used to say this, like when you're doing your real assembly programming, you do not have access to EIP directly. You cannot say, put something into EIP. But over here, we will assume you have programmatic access to EIP, right? So we're just going to say that you can actually treat it like any other register that you've been working with so far. How can you implement return using other assembly instructions, assuming you did have access to EIP? What would you do? So what do we like? If we take at number 2, what's it say that we want to do? Take the value off the top of the stack and place it into AP. Do we know of any other instructions that take things off the top of the stack and put it where we say to put them? Specifically off the top of the stack. Pop, right? Remember, pop takes the value off the top of the stack and puts into the destination. So what could we put here to do the equivalent? So I'm going to take the value off the top of the stack and put it somewhere. So that's pop. And we want to pop it into EIP. That's all Ret does. So if the value on the top of the stack is not where you want to return to, what's going to happen? If, for example, the value 13 was on the top of the stack and we did a ret, what's going to happen? We're going to go to location 13 in memory and start execution there, right? Or if the value 500 is on the top of the stack, you'll pop the value at the top of the stack, 500, and place it into EIP and then begin execution at location 500, right? So when you do your ret, what must you better make sure of?
You have access to EIP.
No, you don't. You don't need access to EIP, right? Because you'll be using ret to go, to ret. But when you ret, you better make sure that your return address is the thing on the top of the stack. Because if it's not, you're going to go to some other random location in memory and start execution there. This can actually be exploited into something called a buffer overflow attack, right? You can declare arrays, say, for example, on the stack, right? If you just say like int 100, int AR 100, square brackets 100, that's going to make 100 integers on the top of the stack. You then might decide to read those values from the user, but maybe you don't limit how much they entered. A good example of this is more with like strings. You declare some space for a string on the stack, and then you do something like scanf, or you use like getS, and it will just keep reading as much as was entered. But because you don't have enough space on the stack, you just overwrite, and if an attacker is good enough, they can overwrite the portion of the stack that has the return address with where they want to go back to instead of where you want to go back to. And so when all of a sudden your function returns, boom, you go to where the attacker said to go to instead of where you were supposed to go to. Does that make sense? What happens? So back here, if, for example, like there was some buffer overflow attack and this was supposed to be our return address 12, the attacker could overflow the buffer so that 12 gets overwritten with 500. And now when you when you return, you go to location 500 memory and start executing the code that's there. So this can actually be exploited by attackers, which is why you should always make sure that you don't use something like gets or like scanf with %s into an array where you haven't checked that you don't read more than what you're supposed to get. Also, this can happen with things like stir copy. If you don't, instead of using stir and copy, use stir copy and just copy more than what should be there. You can actually overwrite what's on the top of the stack, and then when you return, go to some bad place in memory and do stuff there. So Tuesday, enjoy your long weekend. We will go over the C calling conventions, and hopefully you'll be ready at that point to start your next homework assignment after that. See you in office hours if you're coming. Otherwise, see you next week.
How about a question?
1 second.